Okay, so in section 10.2, we talk about derivatives of vector functions and integrals of vector functions. So I'm just going to give you a guided tour here, a quick guided tour of, and then we're going to look at some examples. So they talk about later in the chapter, they talk about using vector functions to describe motions of planets and other objects through space. Okay, that, but that's later in the chapter. Okay, so all right, how do we define the derivative of a vector function? Well, remember, look at, like, they give the definition below, and it's defined in much the same way as for a real valued function. You're taking the limit of a quotient vector. You're taking the limit of a vector, but what you're doing, this, let me highlight it here, this derivative of your position vector r, it's the limit as of the difference of the position vectors r of t plus h and r of t divided by h, and letting h goes to 0. And there is a geometric significance to that definition. It really, honestly, makes a lot of sense, because the vector r of t plus h minus the vector r of t can be thought of as the secant vector. I mean, here's a picture here in figure 1, where they draw in part A, okay, figure 1a, they draw two vectors, two position vectors, r of t and r of t plus h. And then they take the difference between those two vectors, and you know how to add and subtract vectors. So the vector r of t plus h minus r of t is the vector that goes from point P to point Q. And how many remember that? I mean, that's a secant vector, but how many remember, like, for just when you learned in Calculus 1, like when you learned about secant lines? How many recall secant lines, where you would have 2 points on a function and draw a line segment between, or draw a line, I should say, passing through the 2 points, and you called it a secant line? How many recalled that from Calculus 1? Yeah, Ryan does. And then the limit of the secant lines as h goes to 0 becomes what? It becomes the tangent line. There's an analogous phenomenon here with the space curve. You have a secant vector, and as you I want to say this the right way, as you take the secant vector and divide by h and let h go to 0, you're going to get a tangent vector r prime of t, as they show you in figure 2, in part B of figure 2. So you know, why? I mean, it makes sense that the position vectors r of t plus h and r of t would approach each other, and the secant line would approach a tangent, look more like a tangent vector, that r prime of t there in figure 1b. So let's see if we can be comfortable with that. I mean, let's talk a little bit more about this tangent vector. So first thing is, they say, all right, well, how do you find the tangent vector, the tangent of your position vector? Well, the position vector, which is your space curve, r of t, you know your component functions. those component functions, f of t, g of t, and h of t, are the parametric equations for your space curve. And if you differentiate each of those parametric equations with respect to t, you will get the derivative of your vector function, r of t. Space curve, vector function, same thing. So they have a little proof here, which is pretty cool. What they do is they instead of letting h go to 0, they let delta t go to 0. Delta t is the difference in times. They have r of t plus h. Instead of r of t plus h, they have r of t plus delta t. Okay, and you take the limit. So how many have seen that kind of definition? Well, I want to be a little bit careful here. This is fine. This is fine. Let's just look at the derivative. So they show how to get why they show why the derivative of the parametric functions of the space curve form. I'm going to say this right. They show you why the derivatives of the parametric functions of the space curve form the components of the derivative vector. That's what they're doing here in this proof. Are there any sort of questions regarding that proof? Sometimes it's best just to look at the proof, and I mean, are there any questions on that? Deodath, you don't like the proof? Where are you uncomfortable? Where are you uncomfortable with the proof?
No, I like the proof, but I think when you actually do the working, it becomes confusing at times.
Is it just because of the how they bring the limit inside the vector?
Yes.
The limit of well, when you take the limit of your vector function, or when you take the limit, you're taking the limit of these the vector whose each component is it's, well, I want to say it the right way. I tell you what, I'm going to let you all look at that on your own. I think you'll get comfortable with it if you have a little more time to look at it. But let's go ahead and get to some examples here. Let's go ahead and get to some examples. Because I think the examples will help you feel comfortable with the actual definition, with the actual proof. So in example 1, they want you to find the derivative of this vector function, and then they want you to find the unit tangent vector. Okay, so, if you don't mind, I'll call the r of t a position vector. Okay, I'll call it a position vector. There are a lot of space curve, vector function, position vector. They're all stand for the vector r of t. So if we want to find the derivative of the position vector, you just take the derivative of each component, and that's the derivative of your position vector. On the other hand, if you want to find the unit tangent vector at t equals 0, well, anytime you want to find a unit, if you have a vector and you want to find another vector that points in the same direction but has length 1, you just take the vector and divide by its length, and that gets you a unit vector. So the unit tangent vector at 0 would just be the derivative of the position vector at 0, t equals 0, divided by the length of that position vector. Okay, I mean, are there any Are there any general questions regarding the first? Let me see if I can get that highlight off here. Hold on. It does strange things sometimes, you know. When I want to highlight, it sometimes just doesn't highlight it. But at any rate, are there any questions on this first example? Okay, let's look at another example then. Let's look at another example. Example 2. Okay, for this space curve, they want you to find the derivative of your position vector, which is r prime of t, and then sketch the position vector at t equals 1 and the tangent vector at t equals 1. So what they do is they compute the derivative of your position vector, and then they compute the derivative of that position vector at t equals 1. And then they draw it. They draw it. They draw a picture of your position vector r1 and the tangent vector r prime of 1. So the position vector r of 1, if you take 1 and substitute it in, you're going to get the vector 1, 1. So the coordinate 1, 1. Do you see how then the tangent vector r prime of 1 has components 1/2, -1? Do you see how that derivative vector is tangent to the space curve? The red derivative vector in figure 2 is tangent to the space curve at 1, 1. Is that, yeah, thank you, Ryan. Thank you, Diadath. Thank you, Robin. Incidentally, what is the derivative of a position vector in physics? Has anybody learned that? In physics, the derivative of the position vector r. That's good, Robin. That's the velocity vector. Okay, and we'll be getting into that in section 10.4. But are there any questions in general before we move on here? Okay. Okay. Well, then what I'd like to do is bring up a few examples of my own. So on that note, I will do that. And let me give you a moment to copy down this example here. Okay, take a moment. Okay, so here we want to find, sorry, parametric equations for the tangent line to the space curve that has these parametric equations. Okay, those parametric equations. And we could actually use the program you learned in section 10.1, the MATLAB program. We could graph this space curve to see what it looks like. Okay, we could. It's definitely a self-contained space curve because the x, the y, and the z, you know, it isn't like they recycle themselves. It's circular type behavior. So the space curve isn't like going out into space, into infinity. It's restricted. But at any rate, we want to find the parametric equations for the tangent line to this space curve at the point root 3, 1, and 2. Okay, that's what we want to do. So I find it very handy to you know, draw a picture. Okay, so if we're talking tangent line, if we're talking find the tangent line, what's going to be involved if we're going to find the tangent line at a point? Tangent line to the curve, and really they really mean well, no, that's fine. That's fine. What's going to be involved here? In calculus, when we find tangents, derivatives, that's right. So why don't we look at a little picture that'll help us here? Okay, so here I have a little picture. I've drawn just some space curve R of t. Okay, I've drawn a space curve here. I like to shade my space curves in red. Okay, and let's say that this point here is the point root 3, 1, and 2. Okay, well, I want to know, I want to find the tangent vector r prime pi of 6. R prime pi of 6. Now let's think for a moment here. Let's think. Let me see here. Let me write down, actually. Let me write down my components of my space curve. Okay, so what was it? It was, hold on, class. Okay, we had 2 cosine of t two times the sine of t and 4 times the cosine of 2t. So how do we know that at this point here, at root 3, 1, 2, how do we know that at that point time equals pi over 6? I mean, how do we come up with that t value? Let me ask you this. What would the cosine of t if, I want to be a little careful here what I write, because, I mean, the cosine of t is a function, but if I want 2 times the cosine of t, for instance, to equal root 3, what would the cosine of t have to equal? Well, okay. Let me phrase it another way. I'm not phrasing it the way I want to phrase it here. Think of it like this. Think of it like this. Okay. So 2 times something equals root 3. 2 times something equals 1. 4 times something equals 2. Okay, so I got to have 2 times root 3 over 2. In other words, this is sort of an aside here, but it's important. What I'm talking about is this coordinate here, this coordinate, root 3, 1, and 2. Okay, 2 times root 3 over 2 is root 3. 2 times what number equals 1? 2 times a half equals 1. And then 4 times what number equals 2? 4 times a half. Okay. So the t value here, this t value has to be a t value because, see, we're differentiating with respect to t. But so we got to find the t value that's going to work here so that we get this point. Well, which one of the components is the easiest to work with? The x, the y, or the z? What component is easiest to work with? That's right, Eric. That's right, John. That's right, Edith. The y. 2 times the sine of t. The sine of t has to equal a half. Sine of t has to equal a half. And the sine of pi over 6 is a half. So t has to be pi over 6. And it just so happens that the cosine of pi over 6 is root 3 over 2. And the cosine of 2 times pi over 6, which is the cosine of pi over 3, oh, that equals, hold on, that equals a half. So, you know, are there any questions on how we got t equals pi over 6 here? Was this helpful, this little blue box? This blue box I wrote here with, okay, good, all right, good. Thank you. Okay, well now, we're gonna save t equals pi over 6 for later, but we gotta, let me see. Okay, Eric has a good point. You specifically bound the function. You're right. There are other values of t that will also satisfy this. Like for instance, like 7 pi over 6, for instance. But normally they want like a value of t between 0 and 2 pi, traditionally. All right, Eric. Good question. Good question. Okay, so we're going to compute the derivative of the position vector, and then we're going to evaluate the position vector at t equals pi over 6. So what we're trying to do is for this vector here, the derivative of the position vector at t equals pi over 6, we are trying to find the parametric equations for that derivative vector, which well, hold on. I want to be careful. No, let me take that back. No. What we're trying to do is we're trying to find what are the components of this derivative vector. What are the components? The x, y, and z components. And the x, y, and z components are going to be -1, √3, and -4, √3. Okay. So we're envisioning a tangent line to the space curve, okay? Tangent line to the space curve is going to be this line here. Tangent line to the space curve, there it is. There's the tangent line. Put it in green for you. Can everybody see the green tangent line? Is that all right? All right. Well, you know, lines have parametric equations. So the parametric equations for the tangent line are going to have to be √3 minus 1 times t, 1 plus √3 of t, and 2 minus 4 √3 of t. So the line passes through the point √3, 1, and 2. Hence, that's how you get, that's how you get the point here, √3, 1, and 2. And then the direction of the line goes in the direction of the derivative vector. And so the components of the derivative vector at t equals pi over 6 are -1, √3, and 4 √3. Okay. All right. Are there any questions on that? Okay. Well, if there are no questions, I will do another example here. I will do another example. All right. Let's see here. Hold on just 1 minute. Let me, hold on, sorry, 1 moment, class. What haven't you done any of in this course so far? Now you've done some, you've done some derivatives, but what haven't you done yet? Integrals. Okay. All right, Ryan, let's do an integral problem. So remember in Calculus 2 when you had initial value problems? You had problems where, well, I want to be a little careful. I don't want to go back to that right now, but let me give you a moment to copy the example down. Okay, so here we're given the derivative vector. We're given the, sorry, let me get the pen out here. They're given the derivative vector, derivative of your position function, and you're given a point on the position function at time equals 0. And what we want to do is we want to find what the actual position vector is. That's what we want to find. So, okay, well, how do you think, how would we get the position vector r of t from the derivative vector r prime of t? What do we have to do to this derivative vector r prime of t in order to find the position vector r of t? Integrate. That's right, Jamal. That's right, Eric. And that's what we're going to do. So what we have to do is we have to integrate this derivative vector. But how would we integrate a vector? How do you think, what would make sense to integrate in integrating a vector? Okay, let me show you how we do it. Okay, and it'll make a lot of intuitive sense. So for our solution, if I want to integrate a vector with respect to t, the way I do it is I integrate each of the components, each of the component functions with respect to t. Okay? So take a moment to copy that down. Okay, are there any, I mean, the way, when I see this, when I see how we're going to integrate this vector function, I mean, how else would you do it? You know, if you're going to integrate a vector function, just integrate it component by component, right? Now, there is one little thing here. I need a dt here. There should be a dt there. I mean, are there any questions on this? Well, okay, so let's start our integration. So the first integral is easy. Okay, the second integral is easy. This is the integral, right, of e to the t dt. Third integral, oh, that integral, the integral of t times e to the t dt. Okay, that there. What am I doing here? What's going on? What procedure am I using here to integrate the integral of t times e to the t dt? Integration by parts. Integration by parts. Remember the integral of u dv equals u times v minus the integral of v du. That's integration by parts. So I let u equal t and dv equals e to the t dt. And I get this here. And just let me know if you have any questions. I think the writing's pretty clear, but let me know if there's anything you can't read. Okay. Jamal says it's not on the screen. Cut off at the bottom. So this is the bottom here, right here. Are you seeing that, Jamal? Okay. Is Christopher seeing it? Okay, hang on. How about that? Is that better? Okay, no problem. Jamal had to zoom out. Okay, no problem. So, okay. So you notice when I do the integration, okay, I mean, you know, the integral, so this the antiderivative here is, I mean, we know that's t squared over 2 plus c1, right? And this antiderivative here is going to be e to the t plus c2. And this here, we established that that's going to be t times e to the t, you know, based off of here, t times e to the t minus e to the t, sorry, plus, say, C3. Okay, so here's the t squared over 2. Here's the e to the t. Here's the t, e to the t minus e to the t. And here, right here, we have a constant of integration, but it's a vector. It's a vector. Notice there's a vector symbol above it. Why is it a vector? Why not just have a big C here? Why not just say, okay, C1 plus C2 plus C3 equals that big constant C? Why do we have a C vector? Can you tell me what that C vector equals? Can maybe somebody chat it out?
Is it a constant?
It's a constant vector. It's a constant vector, Diodath. But where does it come from? Why is it there? You know, why is it there? What does it equal? I'll give you a hint. It equals, I mean, well, it's a vector. It's a vector, right? So, okay, well, all right, it's a vector. So it's going to equal something times, sorry here, I got to be a little bit, hold on. We're going to do it right. It's got to equal something times I plus something times j plus something times k. Can you fill in the spaces? What goes in the spaces? Well, eventually maybe, but Ryan, right now, the constant vector is not determined yet. There we go. Good, Eric. That's what I'm looking for. Yep. C1 times the vector I plus C2 times the vector j plus C3 times the vector k. Because remember, up here, you know, the constants are multiplying a vector or vectors. This is multiplying the k vector, by the way. All right, is this okay? What this is C3 here. Hold on, let's make it nice. Please let me know if you're uncomfortable with that. Please let me know. Who is uncomfortable with the fact that this constant vector here, I mean, is anybody uncomfortable why it equals C1 times vector I plus C2 times vector j plus C3 times vector k? Or who's very comfortable? I just want to make sure before I move to the next page. Okay, good. Okay, well then let's go to the next page here. So okay, Well, now what we're going to do is we're going to solve for that constant vector. Okay, we have an initial condition that at time equals 0, r of 0 is equal to 0i plus 1j minus k. Well, no. What we're doing, what are we doing here? We're substituting in. Well, no. We were. Hold on. Now wait. Let me start again here. We were told in the beginning that at time equals 0, r of 0 equals I plus j plus k. Okay? And what we're doing here is we're putting in t equals 0 in the position vector. So this means here, 0 squared over 2 times I, right? Plus e to the 0th power times j. Hold on here. Plus 0 times e to the 0. So I'm substituting t equals 0 in the r of t position vector from the previous page. Okay, so 0 times e to the 0 minus e to the 0, k. That's how, plus the c vector. So this here is how we get this here. Okay? Was it helpful my putting in that step? How many found that step helpful? Okay, good. Thank you, John. The book leaves steps out. I'm putting them in. Okay, so we determine then that the constant vector c is equal to the vector I. Okay. It's really like solving an initial value problem. In Calculus 2, you had some differential equations, some basic differential equations where you solved it for initial values. Oh, I'm sorry. C will equal the vector I plus 2k, because this negative k we bring over, okay, over to that side. So hence, we get our final answer, and we can then write the final answer like this. This is the position vector r of t, completely specified. Okay? Are there any questions on that? How many think it's kind of cool? Kind of cool what we just did here, integrating a vector. Yeah, and I'll tell you, if we were to integrate the velocity vector, if we had a velocity vector and we integrated it, what would we get back? When you integrate velocity, what do you get in physics? Position. You get position. The magnitude of the velocity vector, Christopher, is speed. But if you integrate velocity, you get position. So, this is going to come up. See, we got to work in three-dimensional space, so we need vectors. Are there any questions? I want to briefly talk about the orientation quiz here. I'm going to show you it, but are there any questions? Okay, let me stop